For today, we have an agenda like this. We will speak about the platform capabilities and overview of what we can do first. Then we will continue to speak about the core parts of the platform and what is under the hood, such as common interface components, which actions we can execute, a little bit about accounts and service levels. And then we will continue about each individual entities that the platform operates with, such as material structures, simulation workflows, calculation jobs, and speak about what we can do with those. All right, so without further ado, let's start with the platform overview. As we can already guess, today we are entering the era of data-driven science. And unlike experimentation, theoretical science, or the computational science, data-driven science requires new kinds of tools that help us organize the data that is produced by all of these three different approaches and prepare ourselves for the applications of machine learning and artificial intelligence. And that's the reason why we need a framework that can put together multiple different simulation tools, multiple different kinds of data structures, and multiple different kinds of people to collaborate and produce data coherently. And how do we start about building such a framework? Well, first of all, we have to start with a focal point where all these technologies and all these different kinds of people can meet. And we identify such a focal point as the cloud. It doesn't necessarily have to be a public cloud. It could be private cloud. It could be something that is accessible within a specific organization only. But it has to be a focal point where people exchange data, exchange insights, and that's what we call the cloud in this case. It has to support computational scientists, experimental scientists, data scientists, and as well as IT administration and management. It has to support multiple different simulation tools, be either produced in-house or open source or commercial. And it has to be able to sort the results and build a data platform that can be further used to build artificial intelligence. And of course, last but not least, it has to be secure so that any kind of data that we produce in it is the intellectual property derived from this data is secure as well. And that's exactly what we built at exabyte.io. And we start with developing a set of open source components. Open source components that include things like data standards, extractors, and applications, and a set of contributors that help us develop this functionality further. We identify main entities that we operate with. Since we focus on materials and chemicals R&D, we work with material structures, we work with simulation workflows and calculation jobs as main entities. And we identify the data structures that can hold information about those entities. Excuse me. And we define the data structures using JSON schemas as a well-established format used on the web, and make it available as part of a GitHub repository. So JSON schemas that define each of these different entities are available online, and we'd like to make it into a unified data standards source that we can work together on developing. Extractors are software components that provide the functionality to convert data that was produced from other sources into SE, into this standard that I just explained. And applications allow users to utilize these data formats to be able to create or modify the entities that we define. So what we do then, we take these open source components and we deploy them as part of the exabyte.io platform online, so that anybody in the world can navigate to platform.exabyte.io and access these components in a coherent framework where they work together. And we start with the computational material scientists as the most well-known to us usage scenario. And here you can see that computational scientists can use tools that are familiar to them. And through extractors, the data is processed and stored inside the database so that it can be visible to other users within the organization or potentially other people around the globe, so that they can exchange information, they can collaborate on using these computational tools. As a next step after that, we incorporate support for data scientists and experimental scientists, of course, because it has to be multi-tiered, multi-way exchange. We have to understand which simulations work well. We have to validate them. We have to be able to build data-driven approaches too. And by having these three types of users on the platform, we are able to achieve that. And last but not least, most of the scientists today have external elements that they use external to a platform, such as computational clusters for the computational scientists, laboratory equipment or data platform. And by using open source components, we can incorporate these external elements into our platform as well. Okay, so this is the picture that we use to demonstrate the logical components of the exabyte.io platform. Now, if we think about the digital materials R&D in particular, we can identify 7 components of the R&D lifecycle, starting from designing material structures and progressing toward executing simulations and building analytics. And today we support 6 out of the 7 components, excluding the experimental validation, which we have on the roadmap still in works. So here's an example account page. That's how an account for our organization, exabyte.io, looks like inside the platform. So you can see that there are entities that we track for the account, the entities that I just explained. And there are people that can collaborate on working with those entities. It includes 4 members at this time. Some of them have administrative privileges, as you can see. We can see the infrastructure components that are available to us as part of this account, a little bit of the account information, contact information. And what we can do is we can follow the components of this digital R&D lifecycle, such as we can design material structures, either for semiconductor interfaces, for example, or for chemical reactions, like I'm demonstrating here with chemical reaction coded in for the matched elastic band calculation. Once we have these structures designed, we can proceed to set up a calculation, and we provide a set of template workflows that users who are just starting with the platform can clone and utilize to run some of the most widespread, some of the most common types of calculations. As you can see here, we can, so after we select the material, we can select the workflow and apply it to the material. And we can also select a set of computational parameters to finish the creation of a simulation. All right. Then you can execute the simulation. The computational infrastructure is provided as part of our platform. We can track and assert its successful completion. And at the end, we get the result in the form of a graph or a data point. It could be the electronic band structure, as I demonstrated on the previous slide, or it could be the chemical reaction path for a matched elastic band calculation, as we can see here. For the people who use this functionality on a daily basis, we have a programmatic way to access all of this functionality, designing materials, creating simulations, extracting data. It can all be done using the RESTful API. And we have a Python client that is most convenient today to communicate with the RESTful API. Using this Python client, we can create simulations, as you can see here in this video. Excuse me, we can wait for them to complete. And when they're done, we can extract the calculations data, the calculation results, to be able to build a data frame that we can further use to run machine learning and artificial intelligence on top of. All right. It's common to use Jupyter notebooks, and that's another tool that we support within the platform. So users can navigate to the platform, open a notebook session, and utilize the data that they've been producing on the platform to run analytics on it, or again, to build data-driven machine learning or artificial intelligence engines. Here is a quick example where we can utilize the RESTful API through a Jupyter notebook to extract all materials that have silicon as part of the unit cell. All right. Today we support a set of applications through multiple different access scenarios. The main one is through the web interface. We also support access scenarios through remote desktop and through command line. As you can see, we have Quantum Espresso and VASP that are supported through the main web interface and through command line. And LAMPS and WKM, CPTK, GROMACS, TUBEMOL, EM2K that are supported through command line only or through remote desktop as well. On top of the actual simulation engines, we also have a set of analysis tools such as VMG, XCrystal, Vesta that help analyze the structural information and process the data and the results. And we, of course, support scripting applications such as Bash or Python. And that allows us to couple multiple different simulation tools together, either using Python or using Jupyter notebooks or using Shell. On the command line, we utilize modules environment, and here is how the modules that we support today look like in the platform. For the people familiar with the command line approach, we support batch scripting, so submitting calculations using batch scripts. And here is another example of how this can be done. More information about this is available in our online documentation. So you can follow the examples and tutorials to create command line jobs. But here is a quick example. We would use a right-hand sidebar, use the terminal connection through the web browser, and then modify the batch script, adjust some of its parameters if necessary, and submit the calculations for execution, and then wait for them to complete and extract the results. Right, so this is a familiar command line based access for many computational scientists. All right, so let me summarize here midway. exabyte.io platform is a comprehensive ecosystem for materials and chemicals R&D. The goal of this ecosystem is to transition today's fragmented, siloed approach to the fair, findable, accessible, interoperable, reusable infrastructure, ready for the data-driven science of today. The goal of the platform is to supercharge computational scientists by providing a dedicated environment where they can collaborate, they can exchange, they can organize the data better. The platform can be accessed through multiple different access scenarios that include web interface, the command line access, the infrastructure level only access, and RESTful API. All right, now let's speak about the core parts of the platform and what's under the hood. As I was explaining the different components of the platform, you can see that they are also represented inside the GitHub page. So as part of our open source code base, you can, if you navigate to our page on GitHub, you can see the examples of the data standards, extractors, applications, and how we can work with the RESTful API. Again, the three main entities that we work with in the platform are materials, workflows, and simulation jobs. And the relationship between them can be summarized through this diagram. The material and the workflow together form a calculation job, and each of them have a set of properties that can either be present before we execute the job or after. So it could be either descriptive properties or characteristic properties after we do the calculations. And for each of the properties, we also track precision to be able to understand what kind of fidelity we extract when we make these predictions. We separate this concept on purpose to improve the modularity and cover multiple different models, material types, and simulation parameters. This work is still work in progress, so we welcome your contributions. And as of today, the data structures are part of the SC repository, which stands for exabyte source of schemas and examples. And this repository is containing JSON schemas and examples of the schemas, of the data structures that adhere to the schemas. And this repository is also a reusable Python and JavaScript package, which means that people who write their own code in Python or JavaScript can use SC as a way to validate those schemas, to make sure that what they produce is compatible with the platform. Here are a couple of examples. This is how we store a material. This is the definition of the schema. So material contains a formula, a crystal basis, crystal lattice, and a set of derived properties. And here is an example material that adheres to the schema. So this is FCC silicon that contains basis coordinates at 0, 0, 0, 0.25, 0.25, 0.25 in crystal coordinates. And it contains 2 atoms of silicon, as we can see. All right, so this is an example. This on the left is the schema. That's how we define data structures. Inside the platform, it is possible to visualize the raw data, either through RESTful API or even through the web interface. So if you navigate to the list of materials and use the expand as for the action on one of these materials, we can see the content, we can see the data structure that we store inside the platform, the data structure that adheres to the SC standard. So sometimes it contains an additional subset of information that is not readily available in the table. And that's how we are able to see this information. That's how we are able to use it. So every entity that users encounter inside the platform is defined in the data convention that is available and open sourced online. We mean this convention is a unified format that can incorporate multiple different material types, multiple different simulation types, such as density functional theory, molecular dynamics, Monte Carlo, etc. The platform provides a way to access the entities and work with this information in a coherent, easy to access, easy to use scenario. And we welcome third-party contributions. So if you navigate to one of the repositories containing our open source code, you can clone it, work with the repository, make some adjustments, and then submit it back as a pull request on GitHub. We will review the code base, and after we converge on the code review, we can incorporate this functionality into the platform so that you can access it, you can use it online, and we can work on enabling new capabilities together. Now, let's talk a little bit about the user interface and its main components. So the main components of the user interface include 5 parts. At the top, we have the header that is always present, no matter where you are in the platform. On the left, we have the left-hand sidebar. On the right, we have the right-hand sidebar. I will speak about their content in a moment. At the bottom, we have a footer, and we have support widgets in the left bottom corner as well. When we starting with the platform, the most important one is the support widget, to be able to ask questions, to be able to report any kind of problems. And here is how it looks like when we click on the support button. Excuse me. It provides us a form which we can type the questions in. And we strongly encourage users to either attach screenshots or, even better, provide screencasts of the problem, because that explains it better to us and we can quickly reply and suggest a solution. There is also an option to use a chat during the registration process. And sometimes users have reported this chat persists when the users also log in. But we would discourage using this chat functionality for registered users, because we have the support widget functionality instead. So we meant this chat to assist to assist with the registration process only. Okay, so now let's see what we have. Excuse me. Let's see what we have in the left-hand sidebar. To open it, we need to click on the top right corner. And the left-hand sidebar really helps us navigate to the different entities that we track under our account, such as materials, workflows, and jobs. So it's meant as a navigation component that helps us go and visit multiple different entities that we store inside the platform. The right-hand sidebar is meant as a place to access the billing information and statistics about the account. And we can open it by clicking on the username in the top right corner. Here's how it looks. We can open web terminal and the remote desktop session as well through the right-hand sidebar. Now, besides the generic components, we also have a set of entity-specific components that can work with materials, workflows, and jobs, and that are more or less similar between those different entities. And we identify three types: Explorer, Designer, and Viewer. And Explorer is where we list all the entities available. So this is a Materials Explorer that contains multiple different material structures and shows some metadata about each one of them. Explorer table has multiple actions, either grouped actions at the top that can be applied to multiple entries, or specific actions per each item as a dropdown. We can also use the search bar at the top to be able to filter the items that are shown inside the Explorer. The second type of entity-specific components is a designer or an editor. That's the component that we can use to adjust the entities. And here's an example for a materials designer that contains the information about materials that we work with in the session, as well as the capability to adjust the structures, to create new structures, to create new crystallographic arrangements, and things like that. And the third type of entity-specific components is a viewer. So once we have designed the structure, we can visualize it and modify the metadata. So instead of modifying the defining parts of the structure, like the actual distances between the atoms or the atom types, which is prohibited in the viewer, we can modify the name, we can attach metadata like tags to it, and we can modify its parameters. Now, let's talk about the accounts and sharing a little bit. So accounts can perform actions on the platform entities, and accounts define the different ways of how users can interact with the platform. So accounts have members, which are humans or users, and they could be organizational accounts that can have multiple members. And there are personal accounts that, by definition, always have a single member. Organizational team accounts, they can grant different permissions to their members. For example, a member can be an administrator, they can be an owner of the account, or they can be a regular member. And depending on the permissions that are given to a regular member, they can either have a read-only access and read and edit access to a particular entity that is owned by this account, or some entities could be omitted from being accessed by particular members. We also have a way to track all the unique entities inside a bank collection, as we call it. So let's say we have a list of materials. For each of the newly created account, we create an example material, which is Silicon FCC as of today. And naturally, with hundreds of users on the platform, we would have a lot of repetition. But the materials bank collection allows us to track unique entities only. So each of these materials which are the same will point to a single entry inside materials bank. The same concept we use for simulation workflows. Workflows that are identical will have a single entry inside the workflows bank. Now, the natural question for this would be, how does the privacy work? And we have a way to subscribe for the private data scenario, where no other accounts are able to access the entries inside in the bank collection, except for the original account that have created the entity. And without the private data access scenario enabled, the data that is created inside the bank is accessible by other accounts as well. So this is a two-tiered way to collaborate, a two-tiered way to collaborate in a secure, role-based way. So we first can collaborate within an account, and second, we can collaborate within the platform on the unique entities that we create. To be able to access the bank collection, we can use this shortcut action in the Explorer to import entities from the bank. This is a convenient way to build a collection of simulation workflows by accessing those that either we have pre-created as the exabyte team and made available in the workflows bank, or by accessing the workflows that other people have created before and made public. The functionality that is available for the accounts, such as the private data versus public data, is defined by the service levels. And today we have 4 different service levels, starting from free. That's what everybody gets once they create a new account, going to pro, team, and enterprise. And the features that are available to each of the service levels, the feature set increases gradually as we go from free to enterprise, as it would be expected. For example, things like private data, as I mentioned, things like the number of account members, the limitations on the number of entities produced, and things like that. All right. Okay, so let me summarize here about the core components of the platform. Data standards define the entities or the concepts that we work with, and we define those entities inside the unified SC format that is meant to incorporate the data from multiple different simulation approaches, material types. We provide a user interface to work with these entities and give alternative access methods through a command line environment, through remote desktop, through RESTful API. The accounts is how we manage the communication with those entities by users. They could be shared, they could be personal, they could be sharing information across different accounts within the platform. And features that are available to these accounts are defined by their service levels accordingly. All right. I have a quick break now for the Q&A. Let's see if you have any questions. I do not see any questions as of right now. Since we've started late, I'm going to continue and we can take any questions at the end. Now, let's go through the entities that we work with on the platform one by one. So first of all, when anybody is starting with the platform, they usually have a set of structural information that they work with. And initially, they would need to upload the structural information to be able to utilize it within the exabyte platform. And that can be done by using the upload functionality. So first of all, I need to navigate to the list of materials, to the Materials Explorer, and click on the upload button available in the tools in the top of the Explorer table. And here I'm presented with the upload dialog. And I click on select items and select multiple files from disk. Here I select multiple postcard files that I can further preview to make sure that this indeed contains the information that I need. So this intermediate dialog allows me to modify the files that I have just made available in this intermediate dialog. What we can do is we can attach metadata to one or more of the entries. For example, here I attach 2 tags to the entry number 1. And then I select all the entries and click upload to create materials out of those entries. So when we have the confirmation shown, we can see that new materials are created and now are available at the top of the list. You can also notice that we found that one of these materials that was just uploaded, in fact, already has an equivalent in the platform. And for this equivalent materials, we have some calculation results. So this would be a convenient way to avoid redoing calculations for identical structures. The second option would be to import materials from an online database, such as Materials Project. And to do that, we need to utilize the import functionality. So we can do that again by navigating to the materials list and selecting the import action at the top, and then searching for a particular material formula using the search bar, and then selecting the material that we want to import and clicking the import again at the top. So you can see when this acknowledgement is shown, the material becomes available as part of our account collection, and we retain the metadata for it, we retain the original data that Materials Project provides. If we click on this entry, we can assert that this material, in fact, looks like the one that we want to work with. The third option when creating material structures for an account is to use Materials Bank and to copy the structural information from it. As I mentioned before, there are multiple users on the platform that we have today, and they're constantly producing content that we can search to find materials that could be of interest to us. To navigate to the bank, we can open the left-hand sidebar, click Bank and Materials. And just like in the previous example, we would search for a particular material by formula and select Copy in the top to copy this material to our account collection. All right, so these are 3 ways to work with materials. Creating materials, structural information. There is also a shortcut to be able to navigate to the bank. You can see it here in the top of Workflows or Materials Explorer. Now, in many cases, searching by formula is not enough. And for that, we have implemented the advanced search functionality. And here is how it works. If you click on the advanced search tool action in the toolbar, we are presented with the query builder. And this query builder allows us to build sophisticated queries using logical conditions and keyword search. So in this example, I will utilize a set of keywords, starting with the formula, proceeding with the unit cell volume that we measure in angstrom cube, and also attaching metadata to it, tags. So as you can see, I have started with a set of 4,000 materials, and then I narrowed it down to just one, utilizing this query. All right. If I click on reset, we can reset the query, get back to the full list again. That's how the advanced search functionality works for materials in our platform. Now, Materials Designer provides a comprehensive set of functionality on working with the structures. So once we have structural information imported into the system, in most cases, we still want to modify it. We want to make derivative structures. We want to modify the elements that are contained in the structure. We want to build supercells, surfaces, polymers, and things like that. And Materials Designer functionality is meant to facilitate exactly these types of actions. To open a Materials Designer, we need to click on the Create button in the materials list. And here we are presented with the designer interface that contains 4 main components. The header menu at the top, which allows us to access different actions. We have the items list sidebar in the left that shows us the currently active materials in this Materials Designer session. We have the crystallographic panel in the middle, which shows us the crystal lattice and crystal basis for the structure. And we have the 3D viewer on the right. And the Materials Designer itself, it's noteworthy to mention that it's an open source JavaScript application. So if you're working on a project that utilizes any kind of web technologies, Materials Designer can be reused as part of the project, and we use Node Package Manager to disseminate the source code. I will only focus on a very small subset of functionality. I will only demonstrate to you right now how we can select a material from the account collection to make it available inside the designer session as part of this webinar. To do that, we would start with the menu at the top. So we click on Input Output menu and select Import. And here we are not dealing with any external data. We're dealing with the account collection directly. So to be able to use this functionality, we have to either upload or import materials, just like I've explained previously. Now, to make them available inside Materials Designer, we need to click and select one of the entries. And as you can see, the second material was added to the items list on the left. Now I can delete the first one and focus on working with this new structure. All right, so that's how the Material Designer, the basic workflow for using the Materials Designer. Now let's continue and speak about the simulation logic, the workflows that contain the simulation logic, and how we can utilize it. The most convenient way to start executing or working with the simulation logic is to copy it from Materials Bank. We have a set of template workflows that we designed as part of the Exabyte team, as part of the Exabyte platform administrative team. And we have a comprehensive set of workflows that our users are contributing. So we can copy this information again by utilizing the bank workflow functionality. So just like for materials, we navigate to the bank list and copy one of the entries, one or more entries to our account collection. To be able to design materials or to edit materials, to edit workflows after we have copied them, we need to understand a little bit more about the structure and the way that we represent the workflows. We utilize data-driven approach. So instead of storing the logic as a Python script or a shell script, we store it as the static data structure. And the data structure of the workflow contains two subcomponents, a sub-workflow, and inside sub-workflow, it contains one or multiple units. Sub-workflows, we on purpose limit to a single application and a single model and method that realizes this model. So a model could be density functional theory, a method could be set potential, and that's how we deal with excuse me, I just received a message in the chat that looks like my voice was not heard. I just want to make sure that everybody can hear me. It looks like you should be able to. Can anybody comment on raise a hand to confirm that you can hear me? Okay, great. Yeah, thank you, Amanda. Looks like it may have been a disruption momentarily. So again, when we speak about the workflows and the logic that is included inside the simulations, we have sub-workflows and units to cover as main components of the workflows. And units are the smallest part of the logic that is included into the workflow. And we have different kinds of units. They could be execution units like running quantum espresso or VASP or NWChem calculations. They could be conditional units that branch out and can start different logical successions like for loop or while loop. We have MapReduce units that can allow us to go through multiple different iterations of material structures in parallel. We have assignment units where we can define variables. So really, we provide a comprehensive logical environment where we can retain the context of the simulation and modify it during the runtime. For execution units, we also have a set of flavors that can define and template specific types of functionality. For quantum espresso, for example, we have things like self-consistent field calculations, band structure calculations, non-self-consistent field runs, and for each of those, we have an example. All right, here we have the workflow designer. That's how it looks like. We have the header menu on top. We have the items list, again, on the left that contains sub-workflows. And in the middle, we have the sub-workflow editor, where we can edit the information for one of the sub-workflows that we select on the left. Let me demonstrate how it works. Here, we can add a sub-workflow to the list on the left by using this plus button and selecting apply. Right, so here we have now two sub-workflows inside this workflow, and we can navigate between each one of them by clicking on one of the items in the left sidebar. We can also delete this sub-workflow by using this minus button. All right, so that's how we add or subtract the workflow from a sub-workflow from workflow. Now, to be able to modify the information contained inside the sub-workflow, we need to use this sub-workflow panel and units flowchart. So if you look at the units flowchart, it contains the units and the logical succession in which these units are executed inside the workflow. And as you can see, the units have different types, such as an execution unit type. That's the only one that's present in this particular sub-workflow. And the implementation that we have on the platform today is still a proof of concept. And that's why really the right way to visualize the progression on the right, for example, would be to have the flowchart that I demonstrate on the left. So that's how a convergence workflow would look like in our platform today, where we would start with the initial guess for the number of key points, the sampling points for a key point grid for quantum espresso calculation. And then we will run the total energy in a loop to be able to converge and increment the value for the key points by 1 in each of the iterations of the loop. And finally, when the condition of the threshold is passed, we can exit the loop and we can assert that the value of total energy or the value of some other property that we track is converged with respect to the sampling of the brilliance. And we facilitate this type of calculations already today. Now, if we dig deeper and open one of the units of the workflow, we can see that we track multiple different metadata points about these units, such as the application information, the flavor type, the properties that are extracted within this unit, the monitors that are extracted during the calculation, such as we post the standard output back to the web application. We demonstrate how the convergence graphs proceed to make sure that the calculation converges. And at the bottom, we have the input templates section where we can see the actual content of the input file. And instead of utilizing the exact content in a textual form, we first define it as a template that contains variables that can be fed from the data that we store in the database. So the data that comes from the entities like materials can be further fed to this input file, and that's how we get the final input file for the calculation to run in the infrastructure. And we utilize two different render components. First, we render the input files on the web, but as you can see, there are some variables that we still leave unresolved. And that's because we render this structure, this text again the second time when it arrives at the compute infrastructure. It's really not a concern for the user which calculation directory the job is going to run in. They should focus instead on the materials data, on the logical information that is contained inside the workflow, and things like job working directory we can substitute during the computational runtime. Retaining the capability to pass variables between the workflow units also allows us to do things like convergence and loop and modify the workflow context during the runtime. So there are two rendered times, first on the web, second during the calculation. All right, I'm running a bit over time here, but let's try and go through the last part of my presentation for today, the simulation jobs. And before we start, we need to understand that we have created a material already, whether we have already created a simulation workflow. We need to make sure that we have enough balance to perform the calculation. We have enough account credits to be able to run the calculations and utilize the computational infrastructure. We need to make sure that we have enough disk space, and we can then navigate to the left-hand sidebar and go to create a job to open the jobs designer. And inside the jobs designer, we can have 4 main components that we need to work with. The header menu at the top, a materials tab, the workflows tab, and the compute tab. And each of these 3 are self-explanatory. In the materials tab, we can select one or multiple materials. To do that, we need to select the menu dropdown in the header, click select materials, and then select one or multiple entries from our account collection. All right. As you can see now, 6 materials are present inside the jobs designer session. And to be able to understand which material correspond to which job corresponds to which material, we also have a helper in the job name, which will be resolved to the material formula. So once we have finished with the job designer session, we can create 6 different simulation jobs, and for each one of them, the formula will be according to the material formula that is used for this job. Equivalently, we can select a workflow from the account collection by navigating to the list of the workflows and selecting one of them. Here, I'm selecting the phonon density of states workflow and applying it to 6 materials that I have previously selected in the materials tab. And the third component of the jobs designer is the compute tab, where we can select things like the time limit for which we can run these calculations at maximum. We can select the computational infrastructure, including the number of nodes, the number of computational cores per each node, and whether we want to receive notifications. We have a comprehensive set of different types of hardware that users can select from, including different cloud providers, including different types of computational resources. You can consult our documentation to get a more detailed view about those. For example, we have different queues that can support GPU resources, they can support increased memory calculations, and they can provision high throughput infrastructure quickly, or they can be utilizing resources one by one. That all is explained inside our documentation online. So once we have the material, once we have the workflow and the computational parameters set for a job, we can save it by clicking the Save button in the header. Here we go. And what happens then? What happens then, I'll demonstrate in a moment. A few notes about the job creation. First of all, we on purpose disabled the modification of the workflows inside the job designer to assert the data consistency. If we were to modify the logic that is included in the workflow and do that during the job creation, we cannot really assert that we in fact dealing with the same executables, and the data consistency is affected this way. So we disable this functionality. What we allow users to do instead is to create a new workflow. So they first need to navigate to the workflow designer, adjust the workflow, and then apply this adjusted workflow during the job creation. That said, we still allow the capability to edit the rendered text of the input file, but we would discourage users from doing that. We have a way to select multiple materials inside the job designer and create either a high throughput calculation scenario when we create multiple jobs, one for each material, or we can have a multi-material job, for example, a matched elastic band calculation, where we can select multiple different snapshots of the chemical reaction inside a single job, and then utilize those snapshots to study a chemical reaction from beginning to the end. We have the functionality to span jobs inside the jobs and create chained calculations. We can cover those during the advanced topics webinar. Okay, so once we have created the job, it is initially in the pre-submitted state, shown with the light blue P icon here. And we can then select it, click Run, and submit it for calculation. It will change color from bright blue to dark blue, and the status will be submitted. And momentarily, it will also change the status to active. And that's because we're using the debug queue, where we, on purpose, keep extra resources always on the infrastructure. So the debug calculations should be started momentarily. As you can see, it gets started within 8 seconds in this case. Excuse me. And if you want to track the progress of the job, we can navigate back into it by clicking on its name. We can see that one of the units of this job is now active. It posts back the standard output. It posts back the convergence graphs for the calculation. And we can see how the calculation progresses over time. So the active units are shown in orange. The finished units are shown in green. And at the end, when the whole calculation is finished, we can see that its status is also turned green, and F means finished in this case. We can navigate into the finished job and see the results and see the files that belong to this calculation by navigating to the corresponding tabs at the top. All right. So that's how we create a job using a material and a workflow inside the exabyte platform. At this point, I think I'm done with the content. We are a few minutes over time, but let's see if we have any questions. Let's see if we have any quick questions that the seminar attendees can have at this point. There's nothing in the chat. Let's see if there's anything in the Q&A. Not yet. All right. Well, I do apologize for running late today. There was a technical difficulty in the beginning. If you do have any questions, please feel free to contact me either directly at timur@exabyte.io, or when you are inside the platform, you can submit a support ticket, as I explained. We should be able to reply pretty quickly and assist you with the problem. I'd like to thank you for your attention today, and hopefully we'll meet again in 2 weeks, focusing on the advanced topics and working with the entities in the exabyte platform, migrating from using scripts for Quantum Espresso to using entities in the platform. Thank you much. Looks like we do have a question. All right, let's see. We have a question from Ayeli. The application of exabyte is a long-term goal for me to understand and make use of properly. I do not think I'm ready for your Q&A. Thank you very much. Oh, okay. All right. So no question, just a comment here. Thank you, Ayeli. Thank you, everybody else. And see each other in 2 weeks.